I think that's the best introduction I've had so far. I guess I said that on record. Oh, well, OK. Thank everyone for coming. So I'm not quite talking about crowdsourcing today, but really what I want to share with you today is how I've worked to align my work with my values and my hopes for the world, OK? But my hope for this talk is not so much that you walk out of here with my values, but instead that you're inspired to think a bit more about your own values and how to realize them out in the world. And I think that would be really wonderful if that's the outcome of this talk. So with that, I'd like to share with you some thoughts on computational ecosystems and what I think they can do for advancing human values at scale. So I want to start by just noting this question that as I started learning more about my work, what I realized is that all these challenges and questions I was interested in essentially came down to this question. How can we create scalable solutions to human problems and advance desired human values in the absence of a technology that can overcome real-world constraints? Okay, so as a computer scientist and as a technologist, like many of you are, this is a really unfortunate question for me to be asking, right? But it's just the question that kept coming up. Okay, so let me start by giving you an example. When I first got to Northwestern, I began mentoring undergraduate students in research. Okay, and this photo is taken from spring 2014. I started a program called Design, Technology, and Research, and we started with just 7 students. But in about 2 years, I was mentoring over 20 students in 14 independent research projects. And very quickly, I learned that faculty time doesn't scale, okay? Like you could kind of stretch it a little bit, but not really, right? I mean, there's a fixed number of hours in the day. So the general challenge then is how can a single faculty mentor train 20+ students, right? This is the part about scaling the solution to this problem, to cultivate autonomous, self-directed learners, right? So people who are going to do independent work and build new knowledge for science, right? These were the values that I cared about in this project. But in the absence of a technology that scales my time, okay? And this is the real-world constraint because, like I said, can't really stretch it. So as we started thinking about this problem, we realized that it's actually really hard. And the reason it's really hard is that the best human solution, which is awesome, it doesn't scale very well, okay? And the best human solution we know is called apprenticeship or one-on-one mentoring, as you're familiar with. And it's a highly effective model for training people to do complex tasks. But as Alan Collins reminds us, and Alan Collins is kind of like the godfather of cognitive apprenticeship, which is apprenticeship of the mind for skills like research, he says that sadly, apprenticeship requires a very small teacher-to-learner ratio. That's just not realistic in the large educational systems of modern economies. Okay. And we might think that, like some other problems, there'd be a good machine solution, but here, it's really not clear that there's a best machine solution in sight. So software can be used to provide helpful prompts to guide student thinking, but no AI technology can replace the mentor in the foreseeable future, right? And one of the ways to think about that is that to have an AI to do this, you really want a model of how to solve complex ill-structured problems, as you would commonly see in design and in research. And you will want to have models of instruction for teaching people how to do that, right? And we have neither of those two things. So now if you think about what options we have, given this is kind of the state of affairs, we could wait for a technological silver bullet, right? But it could take quite a while, or it might never come. You could imagine instead compromising in a variety of ways. So instead of scaling undergraduate research, you could try to scale lecture, right? You could do MOOCs. You could do those kinds of things. You could train a small set of elite students, right, as we typically do with PhD students. Or you could give undergrads root work. You just say, OK, here's a project. Here's some stuff to do. And that's still good, right, because you're getting undergrads involved in research. Yet none of these options really provide the same learning benefits and scales the values that I wanted to scale. So over the last 5 years, this general question has led us to the design of what I call computational ecosystems. And what computational ecosystems are is that they're systems that interweave community process, social structures, and intelligent systems to unite people and machines to overcome these larger challenges. Okay? So as you can see from this figure, computational ecosystems incorporate many different components. And the goal here is not just to concern us with the design of components, but instead with the design of the entire system. And this focus on a systems approach to design echoes calls from people like Atul Gawande from the Harvard Medical School, who argues that in essence, having great components is not enough. Okay, so here Atul says, we've been obsessed in medicine with components. We want the best drugs, the best technologies, the best specialists, but we don't think too much about how it all comes together. It's a terrible design strategy, actually. And Atul goes on to say that making systems work is the great task of our generation of physicians and scientists. I would go further to say that making systems work, whether it's in healthcare, education, climate change, and making a pathway out of poverty, is the great task of our generation as a whole. We also see this call for system-level thinking in artificial intelligence. So here's Eric Horvitz, who's the director of Microsoft Research, and he says, I'm pretty sure that the next leaps in AI will come from integrative systems rather than wedges, right? So wedges being components or wedges of intelligence. He argues that we need to focus on building a system where the whole is greater than the parts. And closer to home in HCI, there's been similar calls for a need for system-level thinking. So one such call comes from George Furness, who in this wonderful paper called Future Design Mindful of the Morass, which all the students should read if you're interested in designing systems. And he says, it's likely that our designs will be more successful if we became more mindful of the bigger picture, the mosaic of responsive adaptive systems, right? And what he's referring to is that if we're designing applications, we need to think about how those applications fit into the larger systems in which that application operates. Okay. Now, I think it would be really wise for all of us to heed George's words, but as it turns out, we need to do more than just be mindful of the larger system. We actually need to design the entire system for solving some of the problems that I'm interested in. So to design this entire system, we take a socio-technical approach, as you may already be familiar with, but we extend it in a variety of ways to account for the added complexity of having to design the whole system. Okay. So for example, when designing a socio-technical system, we typically do consider the context of the larger system, but in practice, solutions are often created component by component or layer by layer. Okay. So let me give you some examples of that. So for example, we might be thinking about supporting group collaboration and focus on new collaboration technologies for supporting a group, right? Or we might, as many people in the room and myself in the past, think about creating technologies for coordinating crowds. Okay? And this is all great, but one of the things we're thinking about with computational ecosystems as an approach to design is that we're interested in how to bring together multiple structures of people and interactions to jointly solve a problem that gives us new synergies that can arrive when these component interactions inform each other to enable new kinds of solutions. So as another example, you could consider designing layer by layer. Okay, so we might first come up with a process of working, like this is how our group or organization is going to work. And then we might design the social structures for supporting that way of working, and then go on to design tools based on those social structures and the process of work. Right? And this is actually a very thoughtful approach to designing technologies, right? Because you're considering things that are in place, for example, in an organization, and especially if those processes and social structures are things that you can't change. But what I was interested in is thinking about, are there opportunities to design an entire vertical slice as one, right? Where there might be new compositions of processes working with the structure of social interactions and technologies that kind of all work well together and gives you very different designs than if you assume certain things to be fixed. So in essence, what I'm saying is that with computational ecosystems, we're interested in designing simultaneously all the components of a socio-technical system as a single integrative solution. Okay? So we're still going to be thinking about people and technology, but we're going to take a more comprehensive approach where we construct the parts, but also how all the parts interact together, both technically and people-wise as well. And to do this and to reason about the added complexity of thinking about the whole system, we're going to adopt two helpful perspectives in our design work. So one of the ideas is computational thinking, just as you're already familiar with. But we're thinking about computational thinking to decompose and distribute problem solving to humans and machines who could best address them across the entire ecosystem. Okay. And the other idea is something that I call ecological thinking. And the idea there is that we want to create sustainable processes and interactions that support both the ecosystem members, but furthermore, supports proper ecosystem function. Okay. So as I go through my talk and present some examples of ecosystems, you're going to see ideas from this kind of computational thinking, ecological thinking throughout the examples. So for the rest of the talk, I'm going to present two examples of computational ecosystems, one for community-based planning and another one for scaling research training. And then I'm going to preview what's next in computational ecosystems. And then I'll just end with some thoughts on what the role of technology is in advancing human values at scale. Okay. So before I move on to my first example, any questions thus far? Yeah.
Maybe you're going to get that. I'm just wondering, what does a research contribution look like when you're operating at that scale?
Yes. Let me get there with the examples on that one, right? Because we're going to start seeing that there's going to be some designs that look a little different, but give us new principles or system-level principles, I would say, for design. That's not just about how you would design a single component, but how these pieces can work together. So sort of design pattern. Yeah. So one way you could think about it is almost like, what's a design pattern for systems, right? Instead of for crowds or for groups, right? Yeah, that's a great question. Thanks. Any other questions? Yeah, please.
What makes these ecosystems, like what is specific about them that makes you call them computational ecosystems versus just computational systems?
Yeah, sure. I mean, let's go with, can I rephrase your question a little bit? So instead of computational systems, why don't you just call them socio-technical systems? Is that fair? Yeah. Okay, great. So they are socio-technical systems, right? As I was saying, it's the approach to design that's different. Right? So instead of designing component by component or layer by layer, as we might do in the past, we're just kind of thinking about how do you design a system and what kind of advantages you get when you start thinking about the system as a whole. Okay, and I hope the examples as I present them will start to say, okay, there's some things that you could get that's kind of really hard to get when you just design a component.
So the ecosystem isn't the problem, it's the process.
It's the approach to design, yeah, the process or the approach to design. Right. At the end, what you'll see is a socio-technical system. It's a fairly complicated one compared to a single application socio-technical system that you might see in some cases. But yeah, it's a socio-technical system. It is a system. Okay. So given the, did you have a question?
Yeah. Just briefly, to what extent, and you might get to this, so if you are, just stop me. But to what extent in these systems do you think about adaptability or flexibility as far as just being built in, and is there a trade-off between having an adaptability, which I would think would be required?
Great question. Can we save that one for the end of my talk? Because I think after you see the examples of systems, that question becomes really crucial, or something that we might want to think about, right?
Thanks.
Yeah, a great question, and I like where your head's at. Okay, great. So let me move on and give you an example of a computational ecosystem. So first, I'd like to talk about community-based planning. We're trying to design an inclusive process for planning community events that scales and that advances the goal of its members. Okay, so some of you might have seen some of this work on Cobi that I'm about to present in the past, right, or various components or pieces of it. But I hope seeing it as an ecosystem is going to give you some new perspective and new ways of thinking. So the specific use case that we're looking at is planning large academic conferences, right? And what I'm showing you here is a handful of associate chairs, or ACs, working together to try to come up with a preliminary schedule for CHI, right? And this is taken in 2012. And what they're doing is they're trying to construct hundreds of sessions, about 200, over a 2-day period on paper on the wall. Okay, so that's the task they were facing. And immediately you can see that these organizers face some critical challenges. Okay, so the first one is that there's about, I want to say about 10 organizers that are in the room. And what you see is that they lack information about what it is that the whole community wants, right? And what it is that the whole community knows. So CHI's gotten, I think it's probably bigger than this now, but even then it was about 500 papers. And it became pretty hard for any single person or any 10 people to really have a good understanding of all the content. Right? So to even know what papers relate to each other and would make for a good session is something that's very difficult to do at this small group, much less what all the preferences of all the thousands of attendees who are attending might be. And furthermore, the organizers lack tools for managing the complexity of the planning problem and also in resolving conflicts. Okay? So clearly there's some challenges just working on this with paper as the only tool that they had available. But what was even more difficult is when the chairs go home, they put this schedule into a computer. And then they go through this super painful and time-consuming process as they're trying to resolve conflicts where they try to resolve one conflict, right, by moving a session to excuse me, to another place. But then you have to swap, right? So another session goes in its place, and then you create another conflict, right? So you resolve one, you create one. And what they described it as is a terrible game of whack-a-mole, right? Where the moles are conflicts. So it's really unpleasant, okay? And to overcome these challenges then, we created Cobi, which is a computational ecosystem for a new process that we call community-informed planning, okay? And Cobi is built on just two simple ideas. One, engage the entire community in the planning process. And the second one, give organizers tools to manage the complexity of planning and resolve conflicts, right? So these ideas are very simple, but the real question is, how do you do this, right? And that's where we're going to see some interesting ideas in ecosystem thinking. So let me start by talking about engaging the whole community in planning. So to do this, we created new processes and tools for involving committee members, authors, and attendees. So we engage committee members to make the initial sessions right after the PC meeting. We ask authors to tell us which papers fit well in a session with their own paper, but also what talks they want to see, so we make sure those talks are not kind of opposing the session that they're presenting their paper in. We then help attendees navigate the schedule with a tool called Confer, where we are recommending papers and sessions to people, and as people favorite them, we're starting to identify what the popular sessions are going to be, so we could put them in bigger rooms. And then we also could identify talks of mutual interest. So if a lot of people want to see this talk and that talk, and they're at the same time, right, you want to move them so that they're not at the same time. Okay. So far, this is pretty straightforward, right? This is a crowdsourcing kind of problem, and we're thinking about kind of designing for each of these groups of people. But right off the bat, there's actually some computational challenges we need to think about, okay? So if we just focus on committee sourcing for a second and think about the problem of making sessions, one of the things that you must account for is thinking about how to coordinate problem solving, given that there are global constraints, okay? So let me just give you an example. So if you think about a paper, right, a paper could often fit into many possible sessions, right, not just one. But here's the thing. If you collect a bunch of potential sessions, that's not necessarily enough, right? Because the paper is only going to go to one, and once this paper goes into this session, all the other potential sessions that had those other papers, those fall apart, right? So you actually have to think about the interdependencies across these sessions because you have these session-making constraints. So to resolve this challenge, the first core idea I'm going to present is using this two-phase collaborative planning process that involves both a large crowd of all the ACs and a smaller group of about 10 ACs, okay? So in phase one, we're going to involve all the ACs to elicit metadata or possible groupings of papers into sessions, okay? And then in phase two, a smaller group of ACs who are given all these flexible options that were collected can deliberate and discuss in a small group how to satisfy the tighter constraints, right, which are more difficult to do in a crowd. So as you're doing this in real time, right, you might have 200 people kind of tagging and going in at the same time. To manage this process, we have a system called Frenzy, led by Lydia Chilton. And what it does is it uses actionable feedback, which are these things on the left, to tell people what it is that still needs work, right? So it's just telling people, hey, these are things still need to be tagged. These are things that still needs to be put into sessions. But what's interesting about this system is that using the same system, by changing the actionable feedback at different phases of problem solving, you can make it into a crowdware system at first, where a lot of people are participating, and then you're just shifting the feedback you're giving, and then it becomes a groupware system, as you might traditionally think about. And it supports small group working together and deliberating and having these discussions as well. All right, so this is an interesting example of how you can move from a crowd to a group by designing across. So coming back to the general challenge of engaging the community, for authors and attendees, we're going to need ways to give them relevant suggestions, right, of papers that might be similar to theirs, and then for attendees of things they might want to see, right? And you could clearly treat this as a machine problem, right, and think about these as isolated questions, where here you might do some TF-IDF or something like that, and then there you might do collaborative filtering, right? And then you build up a preference profile over time. And that's all very reasonable, and you could definitely do that. But you could do better than that if you take an ecosystems kind of view on this, okay? And the second core idea I'm going to present to you is this idea I call incentive chaining, okay? And the idea behind incentive chaining is that we're going to try to engage increasing sets of ecosystem members by using the data collected in an earlier interaction and seeding it to get further contributions from subsequent interactions and making that better. Okay, so for example, what we do here is that we take the expert categories that are generated through Frenzy by the program committee members, and then we couple it with TF-IDF. to produce a short list of similar papers for authors so they don't have to scan through hundreds of papers to find what's relevant. And in studies, what we found is that having this kind of human expert input with the machine input coupled gives you much better suggestions than if you just do TF-IDF by itself. And then we continue the chain by taking about 10,000 data points we get from the authors as seed data into our collaborative filtering algorithm. And what you get then is you basically skip what's called the co-start problem. Right? So normally in collaborative filtering, you kind of have to like a bunch of stuff before it starts giving you pretty good recommendations. And here you get great recommendations right off the bat, because not only are you getting it from authors, right? It's actually like a double filter, right? Like you got the committee members making these good groupings, and then the authors kind of refined it even further. So we give really good recommendations right off the bat. And then now you have more authors, more attendees participating and going in there and liking things that they like, because they're just seeing it. It's like, oh, I like this, I like this. And we get more data for planning as well. So moving on to step 2, helping the organizers resolve conflicts. With all this data we've collected, we should just feed it all into a computer, hit an optimize button, and get a schedule out, right? No, it's a terrible idea. Let's please don't do that. Okay, and there's many reasons for it. I'm just going to give you 2 reasons right now. One is that the problem is still actually highly underspecified, right? So we end up collecting about 10, 20,000 data points. It turns out that's only a small portion of the specification of the planning problem. And for the parts that the machine doesn't know, right, it's only going to optimize what it knows. You hit the optimize button, and it's easy to get some incoherent sessions coming back from the optimizer that the optimizer has no idea are incoherent, but you don't have the constraints to know that. And this wouldn't be such a big problem, except that the organizers don't even know necessarily that these are bad sessions, right? Because we said the knowledge of what makes a good session is often distributed across the community. So what you get is this problem that to even detect and fix some of the bad things that happen, it's actually quite difficult for the organizers to do if you use this kind of approach. The other thing is that the organizers often have other tacit knowledge or goals. As I'm looking at Manish, because when you're planning things, you're thinking about other goals that maybe are harder to represent in the system or just aren't encoded. You want the organizers to still have that flexibility and control in working with the schedule. So the third core idea then is we're going to take this idea of making a community-based mixed initiative interface that's going to allow the organizers a more flexible way of operating. Okay, so let me show you how this works. So you could go in and you get this multi-dimensional view of the schedule, right? You could look at all these different view options. You could also look at personas, which is something that Kai was very into for a while, where you could look at all these ways, right? And then you go in and these red bars are showing you conflicts in the schedule, both based on hard conflicts and also the community input that we collected. And you could propose a move, and what the system is doing is showing you how many conflicts would be resolved if you made these moves, recommending the ones in green that make the most resolve conflicts, but it leaves the organizer in control to make the decision, right? The system doesn't just make the swap for you. You're still in control to make whatever swaps you want, okay? And by doing this, what ends up happening is that the organizers can work on the schedule with a lot of confidence, okay? So what I'm showing you here is, over time, the red line is the number of conflicts going down, right? That's not surprising, right? You could go in there and then you could get the conflicts going down. What's really interesting is all the activity that happens when the conflicts aren't really going down much, but the organizers are still improving the schedule, right? And the reason they could do that is that if they go into the tool and they have a goal in mind of something they want to change, they could make that change and know if they made that change, how would it affect what community members said? How would it affect the hard constraints, right? So it gives you a way to really apply the tacit knowledge that organizers have while still considering the community input and the hard constraints from the system recommendations as well. So we deployed Cobi at Kai and CSCW in 2012, 2013. And here are the outcomes from those deployments. So the first one is that we have an inclusive process for planning that involved 1,500 people in the planning process. It reduced organizers' time from 100 hours down to 5 hours for planning, which is good. And then organizers produced better schedules by resolving hundreds of conflicts they didn't even know about because they had no way to kind of incorporate the community-based data. So those were some of the outcomes from the study. And the takeaways here, right? I mean, again, I think some of you have seen pieces of this work. The takeaways here is that by thinking at the ecosystem level, we actually get some pretty interesting design insights. So for example, we have this collaborative planning process that could work across crowds and groups. We have a way to chain contributions across the ecosystem, right? Where we take one interaction and then feed the results of the interaction to make another interaction go more smoothly, and so on and so forth. And then we have this way to kind of bring together the system, the organizers, and the community input into one place where we could actually operate on the preferences of a community as a whole. Okay. So before I move on to my second example, any questions on Cobi and community-informed planning? Yeah, please.
So it hasn't been used for the last 3 years.
Yes.
Why is that?
Can I give you the simple answer first?
Of course.
Juho, me, Lydia, everyone else, we all became faculty. And then we ended up...
but it has all these, really positive
Thank you.
things. So,
yeah, so I'll say a couple more things. So Cobi is still used at Kai, but they don't use it with the whole process. They mostly just use the scheduling tool right now. We've been approached by two of the biggest conference planning companies. We're just like, oh my God, like this is the next generation conference planning things. And then they offered us money or to consult and whatever else. And then we're just like, we're faculty. We don't have time. So it does actually go back to question number one. What we ended up doing is we open sourced our code. We shared it with them. We made sure that Kai can still run by having that version of code. And then we kind of just gave it away, really, to the companies. And one of the companies, Confex, they do like the huge AAAS and the big conferences. They're actually currently incorporating a lot of this stuff, which is nice. But like, I don't know if you even call that tech transfer. It's kind of like, here you go. But that's kind of the challenge, right? It's like you have to, there's a lot of pieces and you have to maintain and get these things in.
From an ecosystem's perspective,
Exactly.
right, it seems like a weak link in the chain if the people who design the system are necessary to make it go.
Yeah, well, I don't think it's that the people designing the systems are necessary. It's that it takes a lot of engineering effort to get all the things and work with all the data types and all that stuff, right? So it's not, I don't think they actually necessarily need all that expertise. Now, there is a thing about replicating across sites where you have to think about different communities working differently and things like that. And I think that's a more serious or more interesting kind of conceptual question. But outside of that, it's just time, right? So like, this is maybe not intellectually very interesting, but if I'm going to choose to do a startup, I have to make choices across ecosystems I'm building. And that's kind of what happened here. Yeah. Go ahead.
Could you explain a little bit more on the mixed initiative aspect of the interfaces? I just want to understand what do you mean by mixed initiative?
Yeah, so I mean, people talk about mixed initiative in different ways, right? But humans and machines coming in different ways, right? And here, what we saw in that interface is, right, it's mixed initiative, but it's actually kind of interesting, right? Because it's mixed initiative, but you're operating also on this community data, right? So it's mixed initiative in the ways that the organizer goes in there, they look at something, the machine proposes something, and then the organizer still is in control to think about it, and then the organizer might do something, the machine shows the update, and then so on and so forth, right? It's kind of this collaborative process of working between the human and the machine, right? Maybe the clearest contrast is put it into the optimizer, hit a button, right? Not very mixed initiative. Any other questions? Great questions, by the way. Okay, everyone good? Okay, let me move on to my second example, and then just feel free to stop me anytime if things come up that you're interested in talking about. Okay, so I'd like to go back to scaling research training. I'm cultivating, in particular, this idea of cultivating self-directed learners. Okay, so clearly there's been a lot of effort here on scaling research training. What I'm going to talk about is quite a bit different, particularly around this idea of self-directed learning. And what we found is that if you really want students to be self-directed so that they could do independent research, they're going to need something that's commonly known in psychology and learning sciences as regulation skills. Okay? And what regulation skills are is, given a complex goal or some goal that you have, what are all the cognitive, metacognitive, motivational, and emotional skills you have or you would need to have to reach that goal, right? And for research, the required regulation skills includes things like planning your work and monitoring your progress and replanning as needed, and then also seeking help to overcome challenges as they come up. And students lacking these skills are confined to rote tasks, right? Like they're kind of given something to do, can't self-direct, or they could struggle to make progress where they might hit a blocker and then wait a week until they meet with their faculty mentor before it gets resolved. Okay, and the thing that for me, I just want to point out here beyond the slides is that regulation skills are actually really hard to learn. A lot of students struggle with regulation skills. Okay, I certainly did as a PhD student, and I still do to a large extent. But the flip side of that is, sorry to all the faculty in the room, we do a terrible job of teaching regulation skills. Right, and often what you find, and maybe it's different here, but is that doing research could feel a lot like just bang your head against the wall, and then like one day you figure it out. Right, and I know that's not true for everyone, but I've seen enough of it to think that there's got to be a better way, that we could get better results with more students by helping students build these regulation skills more effectively. So to address this challenge, we created a computational ecosystem that we call Agile Research Studios that provides a model for research training within a learning community. And in this model, all the students, regardless of seniority, conduct independent research and receive authentic research practice, by which I mean the students will go through a self-directed project cycle where they set goals themselves, they learn, they plan their work, they make progress, they reflect on what's been learned, and then they go through this cycle again. Okay. So the core idea here for ARS is that it scales mentor time, right, or faculty time, right? The thing that I said doesn't stretch. So we've already talked a little bit about why apprenticeship doesn't work once you have more than a handful of students. But you might think, why don't we just go with a hierarchical model, right? So have the faculty mentor the PhD students, have the PhD students mentor the undergrads. The challenge here, though, is that as grad students are still learning how to do research, they're novice mentors, right? There's actually a really big difference, as I've talked about a lot in the learning sciences, between being an expert at something and being an expert teacher in that thing. So what happens is that often undergrads working with grad students are still kind of doing root tasks and not really self-directing the research projects. So instead, what we're going to do with this ARS approach is that we're going to take a dispersed control model where we're going to distribute various roles of the faculty member across the entire community so that we could overcome what's commonly known as the 1X challenge, right? So one faculty responding to many students, like I had to do at lunch. Got you guys. Okay. And what ARS is, it's a computational ecosystem for developing regulation skills. Okay. So it's got processes, social structures, and tools, right? So we use agile processes, and we adapt agile processes from software development and design to research to scaffold the self-directed learning cycle. Mentoring is distributed across all these different social structures to support student learning how to plan research work and get help within a supportive community. And then we have these virtual studio tools that support learning through this agile process and that promotes effective interactions within the community. Okay? So I'm not going to present the whole model to you guys, but I'm going to give you a couple of vertical slices to help build intuition. So first, I'd like to talk a bit about student learning to plan research work. So we adapt the agile process from software development, as I was saying, and then students are going to plan their work at 2-week intervals where the goal is to deliver value, but not user value, as you might be familiar with in Agile, but to deliver research value. Okay, and that's something I'm happy to get into a longer discussion about and how we train that and how we think about that. But think about what's the most you could learn about your research project in a 2-week period. And as they do this, we have these SIG meetings. Okay, so SIG meetings is where in a 1-hour period, we have about 2 to 3 student teams who are working on different projects, but in the same research area, roughly, right? You can think about it as one NSF grant, if you like. And then you have a faculty mentor who fades out over time as a graduate student mentor who's in that SIG learns to lead their own SIG. So for example, my PhD students, by the time they graduate, would have mentored about 5 to 8 projects and 10 to 15 students. And they're effectively running their own research lab before they graduate from their PhD. And what happens in this meeting is that we're giving the students feedback on their plans, right? So students come in with a plan, and then we're asking them questions like, well, okay, so why do this instead of this? Like, what are other options you could consider? Are you going to have enough points or hours to do this? Is there a different way to prototype you could think about that might give you the same learning, but with that can actually fit within 2 weeks? So we're starting to develop these regulation skills and planning in these meetings. And to support this process for students recording their stuff and for sharing that with both their peers and with mentors, we have a sprint log. The sprint log is a lot like project tracking tools with 2 differences. So one difference is that it has these questions that help students think about planning, right? And it's actually teaching planning with some of these prompts. Right? And this is something that's often missing in the professional tools because they're not thinking about a learning teaching setting. The other thing, as I mentioned a little bit during lunch, is that we actually cap the number of hours or points students are allowed to put on their sprint. right? So we actually say for undergrads, you can't go over 8 points a week or 16 points a spread. And the idea there is I don't want my students to overwork. I want them to learn how to work within these constraints to be as effective as they can be. Okay, so the goal is not to just overwork. So here's a picture of a sprint meeting. So I have my student Bomani who's presenting, right? And then Lisha is the SIG head. And then all these other students are working on different projects, kind of giving him feedback and seeing what he's talking about. And then that's my dog Stella, who's mostly there just to get petted. But she's also there for moral support and all kinds of other stuff. Belly rubs. Okay, so let me move on and give you a different vertical slice of the problem where we're going to talk about help and collaboration. And the core idea here is that we're going to distribute help across the entire community. So one of the ways we do that is we gather for a 3-hour studio meeting every week, where during that meeting, people engage in peer help. We do demo and critique. We also do some instruction through learning modules, where we're teaching students how to think about making arguments, do study design, like kind of the skills that you would need to be an effective researcher and to have a conceptual model of what it means to do research. And then one of the tools we use in the studio is called pair research. Okay, and what pair research does is it pairs students up to help each other, right, and faculty as well. So let me just show you pair research real quickly. We recently built this pair research platform where you could go in and you could put in, I need help finalizing, so this is for me, right, the intro to my talk. And other people are putting in what they need help with, and then I'm rating how well I could help each person. Right, I could really help those people, and not as much here, right, really help on those things, right, and other people are filling this in as well. And then you go back up, you hit make pairs, confetti falls from the sky. Trust me, that's like, we have that and we have a horse race here too. We can talk about that later, but it's like, this is why we love this tool. Right, and then it makes pairs. Okay, and what the pairs are doing is that it's computing the global maximum weighted matching across the community where people can best help each other. And one way to think about that is that, like for me, for example, for me as a faculty member, if there's a student who no other students can help, it's likely that student will get paired with me if I could actually help that student. And what it's doing then, it's maximally using the distributed expertise within your community as you're building up the capacity of each student to respond to challenges. Okay. Now, just as a minor side point, we actually purposely don't make perfect pairings. We actually perturb it a little bit, just a little bit. Okay, where if you paired recently, you're less likely to get paired again. And the idea is that we try to get more different pairings so the skills distribute across the network a little more quickly. Okay, so that's just a little perturbation we put into the system. So one thing that I want to note, though, before everyone goes, oh, pair research is shiny and it's awesome, is that pair research is great and you'll get benefits using it on its own, but distributed help is not a single app. Instead, it's a helping culture that results from having a whole ecosystem around help. Okay, so what you're seeing on the left is students kind of learning over the shoulder in the lab and hanging out in the lab and learning from each other, getting help. On Slack, we have all these channels for getting help in different areas where people might need help. On the upper right, my students started their own onboarding program for new students. They just started it where for onboarding, there's a lot to learn, and then they have these weekly check-ins with other students. And then as I was mentioning for SIG meetings, in that meeting, students often also identify or discuss how to overcome their blockers, right? So if they hit a bug, they're thinking about who could help them, both in pair research and outside of pair research. And there's a lot of meetup outside of in-person meetings that are structured or scheduled and online as well. Okay. And then on the bottom, what I'm showing you is a small slice of our reflection practice. So every 10 weeks or every quarter, my students do a 10-page self-assessment where they're reflecting on their learning process. And what this question is asking about is just about teamwork and collaboration. And students are thinking about how they could be more effective in giving and getting help for the needs that they have. So let me just show you some of the high-level outcomes from this program in the first 3 years of the program. I've mentored 50 students, mostly undergraduates, in independent research across 25 research projects. And the students won 29 undergraduate research grants from the university, and that's, I'm 100% sure it's the most within the last 10 years, but I'm pretty sure it might be the most like ever. That people have earned. And the students published 11 papers and extended abstracts at conferences like CHI and WEST. And then we have 4 student research competition winners. Most recently, Sarah Lim, who just won the CHI student research competition. So 96% of students stay in the program for at least 2 quarters, but really most, meaning almost all, continue until they graduate. Many of them enter even as sophomores, and they just stay in the program until they graduate. So for quite some time. So the outcomes are really great to see, but one of the things I'm really excited about is seeing evidence that students are starting to develop these regulation skills. So we see students reporting, developing all these different planning strategies, for example, building at the fidelity appropriate for the current stage of the research, prioritizing important features, sequencing tasks, and then in some cases, moving on despite uncertainty, because you do that sometimes. And we also found that students were helping each other a lot, and they were developing in their help-seeking disposition. Okay? So the first stat I want to share is that students help more than 1/3 of their studio every quarter. Okay? And the second stat, or the second quote I have here is just some evidence, right, that students are developing help-seeking disposition. So one student says, I can ask for help, and that everyone asks for help, and it doesn't make them stupid to need help. And you might think this is really silly. It's like, who cares? But help-seeking is really difficult, right? A lot of students struggle with getting help when they need it. And just to see any evidence that they're starting to develop these kinds of dispositions is really encouraging to see. And what I'm showing you on the right is from winter 2016, where each node is a student and each color is a SIG. And what you see is a densely connected graph where people are helping each other in the same SIG, but they're also helping each other a lot across SIGs as well. So coming back to that not stretchable part, the faculty time, it now takes me 10 to 12 hours a week to run this community, okay, and to operate on my research. So 5 hours spent on SIG meetings is actually a little less now, because one of my graduate students effectively kicked me out of the SIG meetings. I actually kicked myself out, because he's ready. Like, he's ready to lead his own SIG. He doesn't need me there. So that's a little lower. And then there's 3 hours for the studio meeting. And then I do normally about 2 hours of in-person help through office hours, and then 2 hours to respond online or for impromptu stuff that comes up. Okay. And then before we had this model, when I had about a dozen students, I was up till 2 in the morning, just about every other day, kind of trying to go one-on-one on all the students. So my life is a lot better. Now, there's some caveats. So for the week before the Chi deadline, my life is not this good, just like all yours are, right? So there's some parts that we haven't quite scaled yet in terms of faculty time, although we do actually have some ideas there that I'm happy to talk about afterwards if you're interested. So the two core things that we're seeing here with this computational ecosystem for Agile research studios, the first is that we're helping to develop regulation skills for research planning and help seeking by using all these different ecosystem interactions across all these people and social groups. And what's interesting to me is that we're starting to extend the scale and the capacity of a community to produce research work, but also to learn, right? And in a way where a single faculty mentor could have never done it, but in an ecosystem you can. Right? And to me, that's just really interesting to think about how the system is doing something that we couldn't have imagined otherwise. And one of the questions that we're really interested in exploring in future work is, how do the students developing these regulation skills help them outside of the studio that they're in? For me, training students with this model, in ARS, with the ARS model, is rewarding, partly because students are learning how to do research. But for me, really, it's because of what regulation skills can do for students once they're away from the program, right? That if they have the regulation skills to approach challenges that they find deeply rewarding, and the skills to think about how to self-direct their own learning to work on those things, that's the thing that I'm most excited about, and that's actually the reason I want to scale this, right? That's one of the big values that I have for this. And in future work, that's the thing that I'm really interested in studying, is beyond school, what are these regulation skills doing for these students? So before I move on to the latter parts of my talk, any questions about Agile research? Geza.
Your retention rates are amazingly high. Do you, surely, you've gotten, there's feedbacks on, what's keeping people, what is keeping them returning every quarter?
It's actually a hard question. I'll say what I think it is, and I actually think we want to do some more detailed studies to really understand why that's happening. So one of which is, as you saw from a lot of this, it's really centered around personal growth, right? It's not just like project, do the project, do the project. It's like, how are you growing as a person? And my students are coming back over and over again because they're realizing what this practice is doing for their regulation skills and personal growth, right, in addition to anything for their project. Now, they also like their project, they keep working on it, and so on. The other thing is this, it's the community. These students, they don't just do research together, right, on their individual projects. They hang out together, they take classes together. They really bond over this community, and a lot of the programs, this gets to the adaptation question you were asking earlier, where a lot of the things, the students are thinking about how to improve this community. They're very invested in making it better. Right? And it'd be really nice to understand all those facets with more detailed study, but that's a great question. Yes, please.
Students who join the lab get new projects. Do you have a list of ongoing projects in each SIG, or?
Yeah, we have a list of ongoing projects in each SIG, and as I mentioned during lunch, at the end of the day, not the end of the day, at the beginning of the day, when students enter the program, they choose. We don't choose for them. They have to choose, and sometimes it comes down to two choices, and they say, just choose for me, and I say, no, you choose. All right, so they take ownership the second they choose. Any other questions? Okay, great. So let me move on a little bit. And then I want to just talk a little bit about what's next as a preview and how we're advancing the kind of system level thinking that's embedded in these examples that I just showed you, kind of thinking about that in broader terms. Okay. So the first preview I want to talk about is thinking about ecosystem level architectures. And what I mean by that is thinking about what are ways to kind of coordinate activities across the entire ecosystem and really thinking at an architectural level how we might be able to support the members of the ecosystem and also the ecosystem functioning properly. Okay. So let me just give you one example of this. We've been working on this area of research that I call on-the-go crowdsourcing, where the idea is to motivate large numbers of people to contribute to solving local communal problems, but through their existing routine. Okay. So what I'm showing you here is someone who went to the package center, who got a notification to say, would you be willing to pick up some packages for other people in your dorm? And she said yes, I guess to 3 of them, right? And then she's bringing it back to the dorm. And what I'm interested in here, one is kind of alternative model for thinking about tasking than the kind of Uber pure economy model, but it's also a way to think about how to connect communities, kind of building these kinds of social capital through these small tasks that are conveniently in people's routines. And that's kind of the value I care about here. But a core challenge in trying to enable these kinds of systems is the need to balance what the system needs to get done and the convenience and the other goals of the individuals, right? And there may be many tasks in many different regions if you're thinking about time banking, or in our case, we're doing a lost and found thing where we had a lost item and then people were searching for lost items for just 30 seconds along their route in different regions. And it'd be incredible, right? If what you could do is people just walk around opportunistically and they get a ping just somewhere determined by the system, but you get globally effective outcomes, right? And that's what we've started to do with this mechanism that we call hit or wait. And what hit or wait is doing, this is my PhD student Yang Sung's work, is if you have these different regions where the tasks are of different importance or value, right? So region 2 is really important. Someone comes over and starts walking to the right, and they're approaching region 3, and you might say, well, you know what? Maybe I should wait. Right? I should wait because there's a good chance the person might reach region 2. Okay? But if they happen to reach region 2, then you might hit, right? And you would decide to give them the task then. And what the system is doing in the back end, it's using decision theory to kind of compute these things in real time, opportunistically as people are coming in, and then notifying them where the system needs are, but conveniently along people's routes. Right? So I just think that thinking about the ecosystem and connecting people in this way in ways that balance individual convenience and also these kind of global outcomes is really exciting, and how these ways of thinking, typically for optimization, use decision theory, can actually enable new forms of interaction and ways of connecting community members. So in another direction, for my second preview, we're starting to think more deeply about mixed initiative, but mixed initiative with humans and machines across the ecosystem. Okay? So let me just give you an example of this that I'm thinking about, where we've been working on this area called readily available learning experiences, where the idea is that you could take any real-world artifact, in our case, websites, but any website, and you could play with it and interact with it and say, I want to learn how that happened. Right? I want to build a conceptual model in my head so I know how to create that and how did that actually work. And on something like Tumblr, if you've been on Tumblr, do you see that scrolling effect? It's like the smoothest thing ever, right? It's like, how do they do that? And I want to learn how to do that scrolling effect. Okay. And this is a problem that people have thought about how to extract relevant code. There's been a lot of work in that in the WIS community. But it's much harder to build a system that can automatically scaffold the process of building a conceptual model for the learner. Okay. So let me just show you how we're starting to do that with a system called Isopleth. So this is work from my PhD student, Josh. And we're looking at a New York City skyline article from National Geographic. Okay, it's super cool, right? It just looks really cool. And what we're showing here is a condensed call graph on the bottom. And then there's these aspect filters on top where you can look at all the stuff that had to do with Ajax, or all the stuff that was tracing across from the mouse events. And as you're looking at this and exploring different parts, you could go in and define your own custom aspects for code that happened after a certain timestamp or whatever you want to put in. And you're now looking at those codes and you're putting in positive and negative filters as you're looking at, OK, well, how do I look at this? Which are parts I might be interested in? And you might go in and click one of these as you're doing sense making. And we're showing you these asynchronous bindings in the purple line. So we actually get the asynchronous bindings for JavaScript, right? Because normally you never know why that function was called in JavaScript. Okay? And then you could go in and label things as you're understanding pieces. And it's like putting together a puzzle where you're doing this iterative sense-making process to understand, that's what this is doing. OK, and then what does that do? Right? So you can start understanding how the pieces of code and components coordinate to make for the whole. And to me, that's a wonderful start and really exciting already. But we're actually going to take a leap where instead of just thinking about mixed initiative tools, we're starting to develop mixed initiative scaffolds that go across the ecosystem. And let me explain what I mean by that. So you have the tool that we used for building conceptual models. But once you have it, how do you build scaffolded exercises that you could just give to people to practice on? So what we do is we take the labels that people generated in the process of learning, and we use that with an automated method to scaffold the next piece of learning, where the student can now do something else, and then we could take that data and then do something else with it to get this closed loop kind of process for thinking about doing self-directed learning on these complex examples that the intelligent tutors are not going to do this anytime soon. Right? But somehow with this mixed initiative approach across these different components, we might actually be able to get there. Okay? So we're just starting some of this work, and I think it's really promising to think about what this might look like. So I want to end my talk by spending just a few minutes talking about the role of technology in advancing human values at scale. Okay? And I want to start this discussion with a couple of clear caveats. Okay? The first of which is that much has been already said about human values. Right? I mean, you should go look at stuff in philosophy, in psychology, and wherever you find your values from. And in HCI, looking at some of Bhatia Freeman's work is really good. Is what I would recommend. Okay? So I'm not going to rehash any of that. And further, people don't share the same values, right? So I'm not trying to say, OK, we're going to design just for this value or that value. And instead, what I want to talk about is this idea of scaling with technology and how that interfaces with our values. And in particular, the point I'm making is that scaling amplifies the kind of compromises we might make when we start scaling with technology. So this is a short story from 1909 that I highly, highly recommend everyone read called The Machine Stops. Okay? And it's written by a guy named E.M. Foster. And he's talking about a world, all right, he's writing this in 1909, that has augmented reality, the internet, and social media. Right? 1909, right? But on one hand, it sounds a lot like the technological golden age of today. But the story wasn't really about that. It's actually about what we've given up about ourselves when we accept things as good enough so that the machine may progress, the machine may progress, the machine may progress to eternity. And there's this part of the story very early in this short story from the boy, and there's just a boy and his mother, the two characters, where the boy's trying to get his mother to come visit him, and she wouldn't, because she's like, what's the point? I could just see you on this plate, right? That was their screen. And then he says to her, the machine is much, but it's not everything. I see something like you in this plate, but I do not see you. I hear something like you through this telephone, but I do not hear you. That is why I want you to come. Pay me a visit so that we can meet face to face and talk about the hopes that are in my mind. So every time I read this, I find it heartwarming and heartbreaking at the same time. And so we are creating incredible machines that scale to do incredible things, but this is an example of a simple thing that we might have missed when we scale. And the question I have for you is the following. Okay? For the values that you wish to scale, the values you care about personally, what are those values? And then what is it that you have technological solutions for with regards to your values? And if they're fully aligned, great. Okay? You're doing great. But if they're not, what do you do? And one of the things I'm really worried about and deeply scared about is how we could just say, no, you know what? Those are not my values. I'm just going to adopt my values to be these technological values of what I could scale with technology. And instead, what I hope everyone to be able to do is to say, no, these are the values I care to scale. I don't know how to do them with technology only, or I just don't know how to do it. But that's the problem we should be working on. And I think if we all worked on problems that we cared about, it doesn't have to be my values, and we try to think about how to do it, even when the technology isn't there, I think that'd be a really wonderful thing. But to do that, it's going to require that we're mindful of our values, what we care about. We have to think about reaching beyond the limits of what technology is giving us. And furthermore, we have to learn to scale. I mean, I really emphasize the word learn there, where scaling is not just more servers or more people. Right? As I've shown you in these examples, scaling is quite complicated. We have to be humble as we think about learning to scale the things that we care about. And we need to build new knowledge and new ways of thinking. And I think computational ecosystems is giving you a slice of that, and it's an important step in that direction. Because if it's about humans, then thinking about ourselves, that it's a part of a larger ecology, is going to be important. And if it's going to be these complex problems, that having computational thinking to bring in all our human and machine ingenuities and put them together is going to be important as well. So with your help, I hope what we can do is to start bridging the ways we embrace design and technology's power with our deepest needs as humans. So with that, I like to thank my wonderful collaborators on the Cobi project for their work on community-informed planning. And my students are incredible, my students in DTR, and have the PhD students bolded on the top, and then my faculty, wonderful faculty collaborators in red on the bottom. And just lastly, the Delta Lab, where I'm one of the co-directors with Liz Gerber, Matt Easterday, Nell O'Rourke, and myself. Liz is a designer and organizational behavioralist. Matt's a learning scientist. Nell's a CS plus learning science person, right? And I'm me. So the way we're able to do work is there's no blinders. Like, I could do stuff that I want to do that align with my values, but I could never do that without learning all these things that I'm learning from them on a daily basis and from their students and our students as well. And I think Stanford's a wonderful place to do research and to be an engineer. But if you're done, or when you're done with Stanford and you're graduated or whatnot, well, we are looking for students, postdocs, fellows, and developers. Okay, so thank you guys so much, and thanks for being a wonderful audience. Probably one question. I want to be mindful. Please.
Thanks. What were your values in the Cobi project?
Yeah, so it's what I said. I said it briefly on the first slide, but it's having an inclusive process where a community can actually advance the goals of all its members. And there's various literatures that inform that kind of value. But great question.
Okay, well, sorry. I want to be respectful. I don't want the sort of trailing out that's rude to the speakers.
No,
so
thanks.
Haoqi will be here as soon as we can finish clapping. So please bring your question up, Kara. Please, I invite you to. And thank you, Haoqi, for coming.
Thank you, guys.